Okay, hello everybody. Welcome back. Today we are going to walk through the next step in our understanding of analysis of variance and talk about a two-way ANOVA. So just adding another factor, another independent factor to our analysis of variance. And so with that in mind, we can kind of take a brief review of what we learned last time. So last time we took a long journey through a lot of graphs, math, and R commands to learn how to run a one-way ANOVA. And then we walked through basically this set of commands. There was a big gap in between getting Ducham's data out of this VOT data set from earlier this semester and then running the ANOVA. I walked you through all the math of how to do that, but the simple way is to just run these three commands by themselves. And I'll do that for you right now and find out that for Ducham's VOT, the average VOT values for different places of articulation depend on that stop's place of articulation. So that's basically what we're getting out of this result right here, which shows us that we have a significant p-value when we kind of model the VOT in this way, such that VOT is dependent on which stop is being produced. Okay, that's a one-way ANOVA because there's only one factor involved in the analysis here. And like I said, we're going to expand that to two factors today. But before we do that, we need to actually take another step to figure out what's going on with data like what we saw for Ducham's VOT there. So you might recall that we started off that little ANOVA adventure by stating that this was our null hypothesis, that the mean value of P VOT was the same thing or equal to the mean value of T VOT, and that was equal to the mean value of K VOT. Basically, there was no difference based on place of articulation for these three stops in VOT, or basically they're all the same. Excuse me. We know now, based on the results of that one-way ANOVA, that that null hypothesis is incorrect. We're no longer going to accept that. We'll reject it, but by rejecting an equation that looks like this, we don't know exactly what we're accepting that's different from that. So we know that the mean VOTs of the three stops are not all the same, but maybe some of these might be the same and maybe some of them might be different. It's not clear. If it was just one equation where it was like mu of p equals mu of t, and we say we're going to reject that, we know that the mu of p, or average value of VOT for p, is different from the average value of VOT for t. But now we've got basically three combinations here that we can think of, and the way to figure out what's going on between them is to run what are called post-hoc tests. So if we want to find out anything more than the fact that these are not all equal, we have to run these post-hoc tests, which are direct comparisons of the means of our three data subgroups against each other to find out which ones are actually different and which ones are still potentially the same. So I'll show you how to do that. It's not super complicated. It builds on what we already know about running t-tests, basically. But I will say before I get into that there are kind of conditions for running these things. As the name implies, you only run post-hoc tests after you have gotten a significant effect in an ANOVA, and you're not going to run them if you don't get a significant effect in the ANOVA. It's kind of easy once you get the hang of how to run ANOVA to just automatically do the tests afterwards, so you don't have to think about it that much. But this is a point where you actually do have to stop and think and say, oh, okay, I got a significant result, I should run these post-hoc tests. Or maybe I didn't, and therefore I don't have to worry about them, and I can save myself a little bit of trouble by not doing this analysis. But we do have a significant effect for stop place of articulation, so we need to go the extra mile and run these tests and figure out what are the differences between P, T, and K for Ducham's VOT data set. So I'm just going to subset out those three stop types here into their own little data frames. And what a post-hoc test is just basically a t-test comparing two of those subgroups. So we're going to look at the VOT for P versus the VOT for T, and we're going to run a t-test comparing the means of those two subgroups. And I'm going to do this in the most simple-minded way available to me at the moment. I'm not going to specify anything about the variance or whether it's a paired t-test or not. I will say, though, if we take a look at these, there are 5 items in each set, and the only difference between the items is the stop that they begin with. Otherwise, they're exactly the same phonologically. So we could run a paired samples t-test here, but I'm not going to, just because I want to keep this simple and focused on just the concept of running post-hoc tests rather than anything else. But yeah, this is a t-test, and so you can interpret the results as we normally do. Looking at this, we see we have a p-value of 0.2683, which means that we accept the null hypothesis. In this case, the t-value is not big enough to reject it. So that means that this mean of x, which is p, so the mean value of p-VOT for Duchamp is 40.86. And we're going to say that's not significantly different from the mean value of t-VOT, which is 57.54. So nothing's going on there. But that's only one of the post-hoc tests that we can run, right? Because there's 3 different pairings of these guys. So there's a little point I want to make sure I get across as well. But unless there's only a subset of specific contrasts you're interested in, then you generally run t-tests for all the possible pairings of the subgroups in your data. So we don't, we went into this saying our null hypothesis is that the mean value of VOT for P is the same as for T as for K. So we didn't think about anything special for any particular place of articulation there. We just said across the board they're all equal. We find out they're not all equal, and we need to find out where the inequalities lie. If it's possible, based on your whatever the hypothesis is for the research you're conducting, that you might just be interested in, say, the differences in VOT for voiceless stops versus voice stops or something like that. So then you might only run post-hoc tests for the voice stop or voiceless stops rather than the voiced ones. We're not there yet. We're just going to do the basics here and just do all these tests across the board. So we have 3 to run. And I'm going to say more about post-hoc tests when we get to the end of the two-way ANOVA analysis after this lecture. But here's the comparison of P and K, which have the biggest difference in mean values. And interestingly enough, or perhaps unsurprisingly enough, we get a significant p-value as well. So that means that these two are significantly different from each other. And if we look at their means, we say, oh, well, K's mean VOT is likely just consistently larger than P's. And if we run this test, between T and K, we get a similar sort of result. The p-value is a little bit bigger, but it's still lower than 0.05. That means that this mean value of Y of the K VOT is significantly bigger than the mean value of VOT for T. So 107 is meaningfully different, or meaningfully bigger than 57.5 here. And I've got the same results here on the slide as well. So basically, these two results are significant. And this one is not. So you can kind of generalize over this a little bit. As linguists, we normally like to, extract generalizations wherever we can. And in this case, you can basically say, well, the K's VOT value is consistently longer than the other 2 places of articulation. So there's no difference between P and T here, but K is bigger than P and K is bigger than T. So K is the one that's kind of standing out here as sort of driving this effect, this overall effect of stop place of articulation on VOT. Yeah, and just stopping here for a moment and thinking about this, you could sort of reanalyze this in a more linear regression sort of way, and if you wanted to sort of assign a quantity towards the different places of articulation and say P is a value of 1, T is 2, and K is 3, something like that, it's just kind of signifying how it moves. The places of articulation move further back in your vocal tract as you go from the front to the back for PTK. And then you could sort of use that as just a gradient measure in the X dimension and compare that to the dependent measure of VOT you get in the Y dimension. We're not doing that here. You might get something significant out of that between P and T. But here we're just saying, look, K's got a longer VOT, and that's what the results of this ANOVA is telling us. Okay, so I've kind of stumbled through that long enough now. I'll point out that you kind of have to do that if you want to make sense of what the results of this test are telling you. And this is sort of also parallel to the issue some of you had in interpreting the results of t-tests in general. Because if you remember when we started doing t-tests, some of you just said, well, I ran the t-test for P versus K and it said that it was significant. And you didn't say which mean value is bigger, that sort of thing, right? If you're trying to figure out what is actually going on in the data, what it's telling you, then you should go that extra mile and interpret which of these groups are bigger than the others. That being said, the usual caveats apply here. So for instance, we only have 5 items per each group here, which is a pretty small sample size. So at that sample size, you start having to worry about things like, well, is the data normally distributed? Do the normal sort of conditions, can we meet the normal conditions for running a t-test, that sort of thing. I'm not going to go into those again, but just try not to forget them as you get into this, because it can kind of start to get mechanical after a while. You could also, as I mentioned before, run paired samples t-tests here, which are usually they usually have more power, and therefore it's kind of advantageous to look at those results instead of the most general Welch correction t-test that you run, or that I just ran. There's also an extra added step that we take here, which we haven't done before, which I need to inform you of. So when running post-hoc tests, the alpha criterion for determining significance is usually made more conservative, or at least that's a very strong recommendation, I guess I would say, in social sciences. So the sort of default way that most people know to do this is the one I'm going to tell you first. And then later I'm going to come back to this topic after we do two-way ANOVA and tell you sort of more liberal ways of doing this that may help you out more. But the basic way, the most default, most conservative way to do this is to apply what is called a Bonferroni correction. I don't know much about Mr. or Mrs. Bonferroni. I'm going to assume that they were Italian. But either way, what they said that matters for us is that you divide alpha by the number of tests you run. And in this case, alpha starts out as a value of 0.05. That's kind of its conventional setting. But since we run 3 tests, remember there are 3 pairings of our places of articulation, we divide 0.05 by 3, and now our new alpha is 0.0167. So we have to beat that to get a significant result. Now, if we go back to our results, we may note that this comparison between T and K does not actually beat that criterion. So this one between P and K is quite low. The p-value is 0.007. This one doesn't change anything because it's 0.268. But this one is lower than 0.05, but it's not lower than 0.0167. So if we apply the Bonferroni correction, then we say, well, that one's not significant. The only kind of significant difference driving this one-way ANOVA effect is the P versus K comparison, and K being bigger than longer in VOT than P. So the other thing I should mention here is that you have to decide which correction you're going to apply before you get into this testing paradigm, right? So you decide, I'm going to run a one-way ANOVA, and then if I get a significant effect for my one-way ANOVA, I'll run post-hoc tests comparing the different subgroups in that one factor, but I will apply a Bonferroni correction to the results, and I'm going to decide that level of alpha before I look at the results of those post-hoc tests. So you're not just, say, going to pick a level of alpha after you look at these p-values from your post-hoc test. You already set the bar before you try to get your test to jump over it. And in this case, the T versus K result is no longer significant. So you wouldn't say that it's significant when you're reporting the results for that reason, if this is the approach you took. So I'll mention, first of all, that why are we doing this? And it's a little bit weird, but again, it's sort of part of the convention of running statistics for linguistics or social sciences research. But when you're doing ANOVAs, you can wind up running a lot of post-hoc tests. So I'm providing you with a very simple example where we have one factor and there are 3 levels in that factor. So you wind up getting 3 possible post-hoc comparisons out of that. But you can wind up running a lot more post-hoc tests than that with, say, multiple independent factors, 2, 3, or 4, even more. And they all may have 2, 3, or 4 levels amongst them. So you can actually, if you do the combinatorics, wind up running a very large number of post-hoc tests. And the worry there is that you might get a lot of false alarms or type 1 errors out of the results of your post-hoc tests if you're just running like 20 or 30 or even more than that, right? So normally our criterion is set so that we only get 1 false alarm out of 20 significant results, or one false alarm out of 20 t-test results. But to try to kind of minimize those even further, we apply a correction like the Bonferroni correction and say, I'll make it even harder to get a significant result. So I can't remember the exact numbers here, 0.0167, is something like 1 out of 60 results maybe would get, yeah, 1 out of 60 results would give us a false alarm. We're only running 3 tests here, so we don't have to worry about that too much, but we're eliminating, in this case, this p-value from being significant. So if it is a false alarm, we no longer have to worry about that because we're not even thinking it's significant anyways. You may pause here and say, well, what if we're doing this in this particular case where we run a lot of post-hoc tests, why don't we do it just all the time? And I'd say that's probably a good point, but that's not conventionally how it's done. So, you can always set your alpha criterion to be stricter if you want it to be. But in this case, normally we're just going to set it to be 0.05 if we're running like 1 t-test, but then we lower it even further if we're running multiple t-tests. Yeah. So I will also note that if you do go back to this Duchamp data and run the paired samples option for the 2 data subgroups of T and K, the one that started out as significant and then stopped being significant when we applied the Bonferroni correction, you'll note that its p-value is actually lower in the paired samples test. Like I said, the paired samples test tends to be more powerful. So this is 0.009. So that would pass either way. But again, you have to decide what kind of post-hoc test you're running before you look at the results, and you have to decide what kind of correction you're applying to the alpha level before you run those tests, so that you can't sort of just like start trying to do different things after the fact in the hopes of getting a significant p-value. So in this particular case, I would recommend not necessarily doing what I did and thinking a little bit more stringently about your data and how it's structured, and just running the paired samples option whenever possible. Again, before you look at the results of your tests. And then in this case, I'll also say that the Bonferroni correction is the most conservative way to sort of correct your alpha value. And there are other ways that are not as strict, but are still valid. And I'll talk to you again about those once we get done with the two-way ANOVA analysis. So there are ways to kind of strategically structure your statistical analysis that is most favorable to you, I guess I would say, but also honest with respect to what the data is telling you as well, so that you don't wind up in a case like this where you have one post-hoc test going from seemingly significant to not significant, and you're like, now I don't know what the heck's kind of story to tell. Because if K is bigger than both P and T in this case, then it's an easy story to tell. If it's just P and K, then it's just like this weird combination of, P has a short VOT and K has a long VOT. So I don't want to dwell on that too much. What I do want to say, though, is that a t-test is an ANOVA. So it's kind of like we're running the same thing twice here, just with different combinations of data. And what I was saying before is that a one-way ANOVA with only 2 levels in the independent factor is the same thing as a 2-sample t-test. So if we combine Duchamp's T and K data, this sort of slightly controversial combination that we've been thinking about heretofore, then I can run a t-test. Well, I've already run the t-test comparing the T versus the K, but now that they're combined into Duchamp TK, I can run a one-way ANOVA, and it should tell me the exact same results as a t-test on that data, but the t-test that I have to run is a variance equal t-test, because variances being equal is one of the assumptions of a one-way ANOVA. So if I look at this, here's my one-way ANOVA, and the only data in this data set are from T and K. I'm eliminating the P's. And I'm looking how VOT depends on stop, and this analysis tells me that there's a significant effect of stop on VOT. The p-value is 0.0145. My F value, or my F ratio, is 9.649. If I do the same thing, well, if I apply a t-test to the same combination of data and specify that the variances are equal, I get the exact same p-value of 0.0145, which is significant again. I don't get my little star, so maybe I don't feel quite as special with the t-test. But it's telling me the same thing. Interestingly enough, I see the degrees of freedom for the residuals and the t-test are the same. My t-value is a little bit different. It's negative 3.1063, but as I mentioned here, if you square that, you're going to get the F value for the one-way ANOVA. And I believe I showed you that when we were wrapping up our discussion of linear regression at the very end when we're looking at how to compare variances, the predictable variance versus the error variance, which is exactly what the f-test does here, and it's basically what the t-test is doing down here as well. Okay, so those are the same thing, it's just sort of expressed differently, but they're going to give you the same results. But kind of the point here that I want to emphasize is that one of the assumptions of the ANOVA is that the variances between the two treatment groups are equal. So just to go back and try to make this clear, we get this F value, this 9.649, by comparing the mean square for my treatment effects to the mean square for my residual. So this is a ratio. 9.649 is 6,215 divided by 644, right? So we're kind of hoping that those aren't going to be equal to each other, that we're going to get more variance in the predicted mean square than we get in the error or residual mean square. So we kind of don't want those to be equal to get a significant effect. But what we're not thinking about here is, well, are the variances of these two treatment groups the same as each other? Because this is basically saying that there's more variance to be predicted in the stop place of articulation effect than there is in just the random variance there. But we don't know if it's kind of the same for T as it is for K. There could be different amounts of variance in those two subsets. And I actually haven't done this. I'm going to do it on the fly, which is always a terrible idea, but why not live life on the edge a little bit? We can, oops, sorry, not the mean. I wanted to look at the variance. And I think actually I did this last time a little bit. Yeah, so in this case, we see that the variance for K is much bigger than it is for T. In fact, it's maybe about 4 times as big. I could actually confirm that by doing this, and yeah, it's about 3.87 times as big. So things aren't looking totally equitable there. If there is a sort of effective place or stop on VOT, it looks like it's might be bigger for K than it is for T. We kind of knew that anyways. But one thing you have to worry about here is violating, whether or not you're violating the assumptions of the analysis of variance paradigm. So ANOVA is going to assume that the variances are going to be equal for each treatment group. And technically, there's some fun words you can throw out there to sort of specify what it means for variances to be equal or not. So if the variances are equal between these treatment groups, between like P, T, and K, then that's the property of that is called homoscedasticity, which is fun to say multiple times over in a very fast amount of time. And an even better word is what happens when you get different variances, which is heteroscedasticity. Yeah, I don't even know how many syllables that is. What is that? 1, 2, 3, 4, 5, 6, 7, 8. 8 syllables, heteroscedasticity. All right, try that 5 times fast. Either way, what we kind of have here between the T and K groups is a bit of heteroscedasticity. So that's a bit of a problem for running an ANOVA with this. I mentioned another assumption that ANOVA makes is that errors are distributed normally about the treatment mean. We kind of looked at that last time, and I'm not going to revisit it too much. And I will say with respect to this issue about variances for each treatment group, apparently it's okay to run an ANOVA as long as the variance of one treatment group is not more than twice as large as any other treatment group. And we kind of are running into a problem with that here. I didn't look at the variance of the P's, but I think it's somewhere in between the two, if I recall. Yeah, so if we're looking at just K's and P's here, that would be reasonably okay, but the T's are small enough and it makes you wonder. So if you do have a problem with this, one non-parametric alternative you can use is called the Kruskal-Wallis test. I'm not going to go into it right now, but I will just say that, keep these assumptions in mind just to make sure you're not misapplying some of these principles or approaches to analyzing your results. And then if it does look like your data is violating those assumptions, then there's always going to be some non-parametric alternative available to you, and that's the one we can use in this particular case. I'm just not going to use it right now because what I want to do before I run out of time is to just review what this paradigm looks like. And I will show you how to do a Kruskal-Wallis test before we get done with the whole ANOVA unit. That's going to come in a couple of lectures. So here's a brief review of the stats we calculate for a one-way ANOVA. We have what is called the residual sum of squares. And the reason I'm walking you through this right now is because I'm going to expand on it to show you how to do a two-way ANOVA. But we start off with a residual sum of squares. Actually, I don't even know if we start off with that because these two kind of go hand in hand. But we split up our total sum of squares between a residual component and a treatment component. And the treatment component basically measures the difference between the means of each treatment group, which I'm denoting here as y bar sub j, the difference between that and the overall mean for the data that I'm looking at, which is just y bar. So I square those, and I do this for each treatment group, and then for each treatment group, I do it for all of the observations n in that treatment group. I'm kind of nesting the summation cycles differently for the two different sums of squares. Hopefully it'll become clear why I'm doing that once we get to the end of the two-way ANOVA unit. But for residual sum of squares, I'm basically doing the same thing, but here I have to kind of take into consideration each individual data point, because the mean of a treatment group is going to stay the same throughout that entire treatment group. But for each individual data point in a subgroup, I'm going to get a different value, and I square the difference between those individual data points and the mean for the individual treatment group. Square those and then sum them, and then I do that for all the different treatment groups from j equals 1 to k. So k in this particular case is the number of factor levels in my one-way ANOVA. In the case we looked at just a second ago, k equals 3 because I have 3 different places of articulation for my stop factor. N will equal 5 because I have 5 different observations within each treatment group, right? There are 5 different words being said with a P, T, or K at the beginning. So on the basis of those numbers, I can figure out what my degrees of freedom are. For the treatment degrees of freedom, I get K minus 1, or it's going to be 2 in this case because K is 3. For the residual degrees of freedom, I get K times N minus 1, so that's going to be 3 times 5 minus 1, which is 4, so 3 times 4 equals 12, so on and so forth, but more generally, this is how you do it. Then I calculate the mean squares, which is the sum of squares divided by the degrees of freedom for the relevant groups, and then my F ratio is the mean squares, where the ratio of the mean squares, where treatment mean square is divided by the residual mean square. Like I said, we kind of only want to look at it in terms of that ratio. Like in theory, you could divide this the other way and divide residual mean squares by treatment mean squares. It's just kind of easier to interpret the F ratio in terms of like how it compares to the error mean square or the residual mean square. And you want that number to be as big as possible, because it means that if it's bigger, that means you're able to predict more of the variance than is just random variance, right? If they're 2 are equal to 1, you're predicting as much variance as is random. If it's 2, then you're predicting twice as much variance as is random in the data, and so on and so forth. So we're always calculating the F ratio this way, even though mathematically it could work the other way as well. But since we're only doing it in this one sort of tailed fashion, when you report the results, the treatment degrees of freedom will always precede the residual degrees of freedom. And I didn't make this specific before, but I can go up here. Maybe we'll do it this way and just kind of plop this in the PowerPoint at the tail end. But for this result here, for the TK comparison, you'd say F of 1, 8. So first degrees of freedom for the treatment, 1, and then 8 for the residuals equals 9.649, and my P is equal to 0.0145. So that's significant. That's how you report that ANOVA result right there. Okay, that's how we do it. That's the math in the background, and that's why we have these numbers for sum of squares and mean squares in the middle here, even though normally we only report everything on the edges of this little table. Okay, so I'm going to leave that there for now, but what we want to do is expand this to a two-factor or two-way model. And so as I get into that, I'm going to remind you of what that one-way model looks like, graphically speaking, and also mathematically speaking. So for each observation of Ducham's VOT, which I'm going to denote as y sub ij, where again, the I is the sample. Ooh, did I do that backwards? Sorry. J is supposed to be the treatment group, and I is supposed to be the sample number. So it's a little bit backwards there, but bear with me. I think this will all make sense in the end. For each observation, the specific value is going to be a combination of these three factors. So we have the grand mean, or mu, which we, if you remember, started off using to calculate our total sum of squares, or our total variance. But then we also have a treatment difference between the stops mean and the grand mean, which we're going to denote in this model as alpha sub I. And then we have a particular random error associated with that observation, which we're going to denote as epsilon sub ij. And the epsilon here is just denoting error, because it's kind of the ancient Greek way to write that short sound, or which we call epsilon in intro phonetics, right? So this is a linear model, basically, and it's basically saying that the observation value, y sub ij, is equal to the sum of these three factors that are all kind of piling into this one observation. So we have the grand mean of mu, and then we have this treatment effect of alpha sub I, and then we have this error effect of epsilon sub ij. And you can think of these first two factors as basically the signal part of this, and this error bit as the noise. And this is maybe the predictable part of it, but we're splitting it up into sort of two parts. So there's a grand mean, which just applies across the board, and then there's a specific value we get for whichever factor is significant in our model, right? So this is going to change depending on what stop place of articulation you're talking about in that one-way ANOVA model that we ran for Duchamp's VOT. Okay, here's what it looks like for just Duchamp's K data, which we have seen already is a bit exceptional in his case. So we have, here's our mathematical model here down at the bottom. We've got these kind of three factors, mu, alpha sub I, and epsilon sub ij. So let's look at it for this one particular data point, which I can't remember if this was which particular production. I think it's call, because it was keel, kale, call, coal, cool. So this one has the highest VOT, and the reason I'm picking on this one is because we can just add our way up to it. It's all positive, and that's kind of why it's the highest VOT value at the end of the day. And so we have the grand mean, which I've plotted here as this blue dashed line. It's something like 68.6, I think. And then when we produce a K, or when Duchamp produces a K, he gets this consistent treatment effect where he adds about 30 milliseconds of VOT to the grand mean, which is why K has higher VOT in general than T or P. And then there's also a bit of a random error. So, sometimes he's above that K mean and sometimes he's below. We just can't predict it, so we just kind of add it in to account for each data point. And that's a fair amount of VOT here, maybe 30 milliseconds of VOT as well. I think we'll find out here in a second. But I just want to kind of emphasize here that I'm making this as simple as possible for you because these are all addition symbols down here in the mathematical model. And we can see that easily if we just keep adding, and adding to get to this data point. But sometimes the random error can be negative. Sometimes it can be positive. And then sometimes the treatment for each particular factor level can be negative as well. So I didn't put that in here, but I believe the actually for both P and T, their mean values will be a little bit lower than the grand mean. So for both of those, you get a negative treatment effect moving down from this blue line to something more appropriate for that place of articulation. And here is the, did I do this right? I think I did. I think this is supposed to be, I don't think that's right at all. So let me double check. I thought I prepared for this lecture. But if we add 68.6 plus 58.8, maybe it's right. Yeah, that's not right. Let me try that again. Sorry. Duchamp K. So this should give us the, yeah, that's where I messed up. I just typed wrong. This is the treatment effect for K. And if we just add those up together, we should get 146.8, which is what we have here. Okay, good thing we have R to do the math for us rather than just doing it all in our heads. But both of these effects of the treatment and the residual error are close to 40 milliseconds. The grand mean is 68.6. So those are pretty big effects overall, which is why we get this really long VOT measure here. This doesn't matter because what we want to do is expand this. So we're going to move on from the model we just saw on the previous slide and figure out how to do a two-way ANOVA. And in this case, for each observation, we have to consider the contribution made by 4 different things. So we have a grand mean, which we've seen before. We also have each factor independently, which we've sort of seen before, but with a two-way model, we will have 2 different factors, right? So it's not just one treatment effect, it's 2 potentially different treatment effects. And crucially, there's also the possibility of an interaction of the pair of the 2 factors involved. So sometimes when the 2 work together or work against each other, you can get sort of a different treatment effect than you get when the 2 are working independently. And then there's still going to be an error associated with each observation. So I'm going to show you what this all means here, graphically and mathematically as well. But crucially, since we're expanding from 1 factor to 2 factors here, the big sort of addition we're making is a distinction between these independent factors, which we'll call main effects, and then their potential interaction, which we're going to call interactions. So the main effects can be significant on their own, and then the interaction could be significant as well. Okay, so this is what it's going to look like mathematically. Before we just had mu plus alpha sub I plus epsilon sub ij. Now we're adding these 2 new factors in here, and then we're also kind of expanding the error term. So we have an observation y sub ijk. It's equal to the grand mean of mu plus the treatment effect, the first treatment effect, alpha sub I. That's for whatever factor 1 happens to be. And then there's a second treatment effect for beta, which is beta sub j. Then also the potential interaction of these 2 effects, alpha sub I, beta sub j, and then this error term, which we have to add a 3rd subscript to because we have to consider 2 factors in addition to just the random error for each observation. Okay, so factor 1 is alpha. It could have it has up to I levels, and then beta has j levels, so that number can differ as well. And then there's the interaction between them, and you get sort of all the different combinations of their levels when you're considering that interaction. Okay, so this is going to be harder to visualize graphically. I put a lot of work into it, so hopefully you appreciate that. But in the old days, I used to write on the board this stuff, and again, you don't want to read my handwriting, so be thankful for what you see in this. But it's all generated by R, and actually the code for it is going to be placed in the slides at the end of the PowerPoint that I'll post online. So if you want to replicate it yourself, you can kind of use that to start with. But what I want to do is to try to make this sort of model work graphically for Duchamp's first production of the word cool, which in our previous slide or previous model was K5. So it's this data point right here, which I think is 90.6. Hopefully you can see that. It's sort of halfway between 80 and 100 there. And you note in this one that we go up for the grand mean, we go up for the treatment of K, and then we actually go down to get to that data point. So there might be a little bit of negativity here. That's okay. We can account for it all in our model. Sometimes you're up, sometimes you're down. All right, so to get this to work, we need to go back to the original data set we had. This is just one of 3 repetitions of the word that Duchamp recorded. And I will tell you that if you apply this model with the 2 factors and the interaction to this sort of data, and let's say your 2 factors are stop, place of articulation, and then vowel is your other factor, where you have 5 different levels, you're not going to get anything meaningful out of a two-way ANOVA out of it. And one of the reasons why, I'll make this explicit later, but one of the reasons why is that you will be able to account for all the variance with just everything leading up to the error term. So you don't need the error term if you have a two-way ANOVA and not any variance left over for each individual observation. So we're going to have to go back and instead of looking at just 1 repetition of each stop and vowel combination like we had here, we're going to go back to the original data where we have Duchamp producing 3 repetitions of each word. So there's going to be a little bit of error variance left over so we can actually calculate F ratios. That's a subtle point. I'll come back to it later, but what I want to do right now is go back to the original data set. And I'm going to call it VOT3 because we have 3 repetitions of each word in this data set. And we need to do a little bit of extracting here, and I'm going to reveal some of the answers before I get to them. But Duchan's productions are here. This doesn't have all the fun stuff like the format frequencies and whatnot, but you see there's 3 different repetitions of each word. And so what I want to do is figure out what's the grand mean VOT for this data set, because what I'm trying to do is account for this VOT, not that one, this VOT value with my two-way model. So we're going to start out with that grand mean, and it's 71.11111, or 71 1/9, I guess. We can also figure out what the mean value of his k-VOTs is. So we're looking at factors of stop and vowel. And the first one, our alpha factor, is going to be stop. So the mean of that, which you'll see both in R and in the PowerPoint, is 101.8733. Okay, so what does that mean? For our modeling purposes, that means his treatment effect for stop, or at least for the K, that specific level of that factor, is 30.76222. So again, to kind of hopefully make this explicit, factor 1, which is going to be stops, or stop place of articulation here, we're calling alpha, but it has I different levels, right? So alpha sub 1 would be P, alpha sub 2 would be T, and alpha sub 3 would be K. And for alpha sub 3, we get a treatment effect of 30.76 milliseconds. We need to calculate a similar treatment effect for OO. So in this case, we will have 5 different vowels in our model. So that beta factor, or factor number 2, is going to have 5 different levels. We're looking at the 5th level here, the effect of OO on VOT in particular, and we find that has a treatment effect of 14.1 milliseconds. So these are our two treatment effects so far. We add both of those to this grand mean, and we are basically halfway through our model. So we've got this so far. What we need to add to that is the interaction, whatever it is, and then also the error term for that particular observation, whatever that is. Yeah, so here's the deal. We figured out these 2 treatment effects for K and for OO. So if we add those 2 treatment effects to the grand mean, then we'd expect the mean of KOO productions, or cool productions, to be the grand mean plus the treatment for K, alpha sub 3, plus the treatment for OO, beta sub 5. And we get a total of 115.97 milliseconds. But when we look at what the actual mean KOO VOT is, we get something quite different from that. So for this, instead of just abstracting out the K's to figure out the K effect, or the O's to figure out the OO effect, I'm going to extract simultaneously the K-OO productions so I can figure out if there's a KOO effect, kind of on top of the K effect and the OO effect by themselves. And lo and behold, if I do that, I find out that there is something going on here. So before, I'm predicting or anticipating a mean value of 115.97. But when I look at what Duchan does when he actually produces cool, he gets a VOT on average of 98.266667. We can actually take a look directly at his productions here. There's only 3 of them. This is why we need 3 different ones. But the VOT is in that range, right around 98.2. Yeah, so this is lower than we'd expect from the main effects, or the independent factors on their own. It's in fact negative 17.7 milliseconds lower than what we get from those first 3 factors that we're adding together. So for this reason, this is going to be our interaction effect right here. So before, with alpha sub 3 for a K, we had an effect of 30.7. And for beta sub 5, or the treatment effect for OO, we had a value of 14.1. To that, we need to add on alpha sub 3, beta sub 5, some combination when those 2 start working together. And that treatment effect is going to be, or that interaction effect is going to be negative 17.7. It's going to be this value here. So just to make this explicit, the difference in the mean observed VOT value of KOO productions and what we would predict that value to be on the basis of the influence of the 2 main effects alone is the interaction effect of K and OO. It's something that happens when they're together that you can't account for by assuming that they're acting alone. So yeah, whatever happens when they get together, it looks different, and so on. We have to add that interaction effect to our mathematical model. And then on top of all that, of course, there's still going to be a residual error when accounting for any individual data point. We've seen that in this sort of combination of three here. They're not all equal to 98.26667. There's a little bit of variance in there as well. And in this particular case, what you just do is you take the first observation, which is the one we're concerned with, and you, I think I did that, yeah, oh no, I see what I did here. So this is the sort of expected value for coup productions, and we find that if we subtract this value from it, we get the actual observation value. So that error term is going to be negative 7.66667. Okay, hopefully that makes sense, but that accounts for our 5 terms in that mathematical model. Here's what they're going to look like. So here's our 5 terms, the grand mean, the main effects, the interaction effect, and the error term. This is what they look like graphically speaking. So here's our data point. It's 90.6. It's y sub ijk. There's our grand mean, which again is 71.11111, so on and so forth. We add to that our k treatment, which is about 30 milliseconds. We add to that our u treatment, which is about 14 more milliseconds. But then we realize when you get those two factors working together, k and u, they interact such that the VOT is actually lower. So we lower that total by about negative 17. And then there's a bit of residual error, about negative 7 something. And that combination will bring us down to our grand total of 90.6 for this individual data point. Okay, I'm going to take a mini break and say, holy smokes, there's a lot of colors on this graph. Aren't you glad that you're not reading my handwriting on the board as I'm trying to explain to you how this all works? There's also a lot of factors in this model, right? So there's a lot of assumptions going into this once we start to get into the two-way ANOVA approach. Okay, so a lot of assumptions are going into this. Do we really need them all? And guess what? We can run an ANOVA to find out which of these are significant, which of these actually matter, and which do not. So the ANOVA approach is going to work the same way for the two-way model as it does for the one-way case. Basically, for each factor and interaction, you're going to calculate a treatment variance or a treatment mean square, and then you're going to compare that to whatever's left over, whatever residual variance you have left over the model, the sort of predictable part of the model can't account for. If that resulting F ratio is significantly different from 1, you infer that that factor or interaction is meaningfully accounting for some variance in the data. And if not, you just leave that factor or interaction out of the model. And I guess I'll add to this point what we learned before at the beginning of this lecture is that if you get that significant effect, you will also have to do post-hoc tests at the end of the day to figure out like what's bigger or smaller in that particular treatment group. Okay, so here's the way it works mathematically. And I'll basically wind this lecture up with this series of equations and then one brief example on the next slide. This is also something that nobody liked to see me write on the board, so I'm glad I'm able to just put it in a PowerPoint like this because it's a lot of math, basically, a lot of symbols. But hopefully it's not going to be too bad when you stop and slow down and just kind of take a look at what it's telling you. So for this first factor, remember I want to come up with a treatment sum of squares divided by its degrees of freedom to get a mean square for that treatment. But the treatment sum of squares is basically what we saw before, where you get a separate mean value for each level of that treatment group and subtract from that the overall grand mean, square that difference, and then sort of sum it up for every single observation in that particular group up to n times, right? You do something very similar for the second factor, but in this case, you're looking at a different set of levels. So this one is, the levels are called I. For beta, oops, there's a little mistake there. For beta, it's J. Glad I caught that before you saw the rest of the math. So yeah, this is and I'll point out here that these are basically the treatment effects, right? So y mean sub, or y bar sub I minus y bar overall, we're going to call the treatment effect alpha sub I. And then y bar sub j minus y mean overall is going to be the beta sub j treatment effect just over here. We'll use those as abbreviations later on. I'll also point out for these main effects, their degrees of freedom is basically the number of levels in that factor minus 1, because that one other degree of freedom gets sucked up by calculating the mean for them. And this is the notation that always caused me problems writing this on the board, but this is an L up here. This is not a 1, this is an L, and that's an M, and we're just kind of go down through the alphabet that way. The tricky part is calculating that that interaction sum of squares. So for the interaction, you have to come up with the mean of those two factor levels together, y bar sub ij, and then you subtract from that the grand mean plus the treatment effect for alpha sub I plus the treatment effect for beta sub j. The difference between those you square, and then you add them up for both combinations of factor levels and then also for each individual observation in those different factor levels. And then interestingly enough, you sort of multiply their degrees of freedom with each other as well to calculate the degrees of freedom for the interaction. But just to focus on this part here, the effect of the interaction itself, alpha sub I, beta sub j, is that mean value for the interaction itself. In this particular case, we found, let's say, when the mean value for Q is 98.26667, and you're subtracting from that basically everything you'd get by adding the first three terms together. So that would be this combination here, the grand mean plus the individual treatment effects for the first factor and the second factor. So you take this combined mean, subtract from that the effects of the grand mean and the main effects, and then you get the interaction treatment, which in this case is negative 17.7. But that's all that this scary looking mathematical stuff is saying right here. We're going to consider that to be alpha sub I, beta sub j. And then again, exactly the same thing for the residual sum of squares. You're just kind of trying to factor out the predictable stuff you can get here. So alpha sub ijk, actually, that's not what I want. I found another mistake. Imagine that. That should be y sub ijk. Yeah, like that. So in that case, you're subtracting from that everything you can predict with the other factors, the grand mean, the independent factors, and then also the interaction between those factor levels. And then you multiply all of those degrees of freedom together, the number of levels in both of the independent factors times n minus 1, the number of items in each sample minus 1. And then you get your overall error term, which is all of this stuff that you're squaring in this equation here. I'm not going to dwell on this too much. I think from the example you can see where the numbers come from, and you don't need to memorize this math or anything like that. But basically, at the end of the day, when you run the two-way ANOVA, you're getting a treatment mean square from this stuff for factor number 1. You're getting a treatment mean square for factor number 2 here. You're going to get a treatment mean square for the interaction. You'll divide all of those by the same residual mean square at the end of the day, get an F ratio for them, and then interpret it based on whether its p-value is greater or lesser than 0.05. So for this two-way ANOVA, you get 3 different F values, you get 3 different p-values from that as well. In practice, you don't need to worry about any of that math. We can go back to this VOT3 data set. I'm not going to load it in again, but this is how you run it. And it'll spit out data that basically looks like what I promised. So first of all, before we look at this data set here, what we have is a model that is saying that VOT is my dependent measure, and my 2 independent factors or main effects are stop and vowel. And I'm just doing this to see if these have a significant effect on VOT or not. And then these are the independent factors. And to also look at the interaction, I specify that they're combined with this asterisk operator. So that means look at both of these independently and also look at them as an interaction. And that's why I'm getting 3 different results here. So for stop, I get an F value of 11.861. That's its mean square divided by the residual mean square. That is a very large F value, much bigger than 1, and so I get a significant p-value. This is a very small p-value here, right? So stop makes a difference on VOT here. Vowel, I get a much smaller F value, which is not significant. So vowel does not seem to be making a difference. And then this is the interaction. So it's a little bit funny because here it's saying, look at this asterisk means also consider the interaction. When I actually get the results of the two-way ANOVA itself, it gives it to me with a colon, which is saying that's the interaction effect there. So I don't know why they use two different operators there. But either way, this is the interaction, and it's F value very close to 1, which is basically me saying that the interaction doesn't account for anything. And I'll point out here, just again with these degrees of freedom, we had 3 stops. So for the main effect, we have 3 minus 1 equals 2 degrees of freedom. We have 5 different vowels. So for the vowel factor, we have 5 minus 1 or 4 degrees of freedom. And then for the interaction, you wind up multiplying those together. So 2 times 4 equals 8. How about that? But either way, this is the only one you have to worry about as being significant. To really do your homework the right way, you'd have to run Posthoc tests to figure out what that means. I'm not going to do that right now. I will point out that you can run the ANOVA without the interaction too. By, whoops, sorry. Yeah, go back to this. And instead of using that asterisk operator there, you can use the plus symbol, which just means consider these 2 factors independently without considering their interaction. And if I do that, I get the basic same result in terms of p-values for what I saw before. You notice there's only 2 rows here, though. There's not this interaction effect. And their f values are basically the same, but not quite. So I get a slightly different residual variance here, and I'm not able to account for some of the same variance in the mean squares here. So the F values work out a little bit differently because basically with this plus symbol here, what I'm doing is simplifying this model by eliminating this part of it here. So I'd only get this stuff as possibly accounting for predictable variance. But you can do that if you want to. At this point, we're kind of getting to the point where hopefully you understand this well enough that you can see that you can just build whatever model you think is most appropriate for accounting for your dependent measure here. And if you are actually running a two-way ANOVA, since we're not kind of totally fluent in how this works yet, don't do this. I would recommend against that. And just as a default way of running a two-way ANOVA, since you don't know any better or worse, always run it with that sort of interaction option in the middle, and then the results will tell you whether or not the interaction matters and whether or not the main effects matter as well. The problem with this example, even though it's easy to understand from a linguistics point of view, is there's no interaction effect. So I want to really show you what an interaction looks like when you get one. All we have here is a significant effective stop, which we've seen before in the one-way ANOVA. So I'm going to give you a different example in the next lecture on this topic. I've talked enough for one video for now, though, but I will warn you that the next example is coming from the world of baseball, which is one of my other passions in life. So if you don't like baseball, I'm sorry. If you don't know anything about baseball, I'm also sorry. But by the time you watch that video, you will understand interactions better. So I can promise you will learn something, hopefully. All right, hopefully you learned something with this video as well, but I'm going to stop for now because, like I said, I've talked long enough. But that's two-way ANOVA. We'll see how it works in gruesome detail next time around.